Thank you for attending this session on effective tools for design analysis and multi-objective optimization. In this session, we will discuss the SDI Tools Apogee software and its application for performing a statistical allocation for a design. The SDI Tools software includes a suite of tools and utilities to support system engineering, design for Six Sigma, and product development. The Apogee toolset is specifically designed and developed to support analysis and optimization activities for design analyses that may be performed in Microsoft Excel. In this discussion, we'll be focusing on the topic of statistical allocation for a new design. The SDI Tools Apogee software will allow you to take a new or existing Excel worksheet in which you've included information for parameters and calculations for responses, and will allow you to assign information to a cell as a parameter and define its statistical properties so you can analyze the effects of uncertainty on a response. Likewise, in the Apogee tool, you can define an equation cell as a response with that's defined by an equation and has an assigned lower spec limit and possibly an upper spec limit for which you're trying to judge compliance with respect to variation of your individual parameters. So with this setup, we can then start performing statistical analysis, and our focus in this session will be that of a statistical allocation. In prior sessions, we've discussed sensitivity analysis, Monte Carlo analysis, and then also the assignment of constraints and goals to different conditions in your design so that you can perform a multi-objective optimization. So now we will investigate how to take a defined design that's specified in a Excel worksheet and perform statistical allocation. The problem that we're going to examine is where we have a second order low pass active filter that we've developed, and we've assigned nominal values to the four primary components that will determine its response, two resistor values and two capacitor values, and we've assigned 5% tolerances to each one of these. Now, in prior analyses, we wanted to determine what was the probability that our product specifications would be met, and we've analyzed the cutoff frequency and the shape Q, and we found out that the design was marginal at best. So we'll go back and review that analysis here in just a moment. We had the equations for calculating the cutoff frequency and the Q, and the key aspect of this analysis was to understand what the variation of these responses would be as a function of variation of the parameters in the design, the resistors and the capacitors. So going back to the Excel worksheet that we set up before with the definition of our individual components, the identification of the two responses that we're analyzing this, and then remembering also that we assigned variation properties to each one of these components that's represented with the blue border. So in this case, for R1, it has a mean value of 18,000 ohms. It's uniformly distributed from 17,100 to 18,900, and this distribution has an uncertainty or a standard deviation of about 519.6. So this is the way we've defined the variation on each of the parameters, and then we performed the analysis, and we saw that the Q response would have uncertainty that would lead to a probability of non-compliance of about 13.7%, and the cutoff frequency has uncertainty that could lead to a probability of non-compliance of about 0.003 or about 0.3%. So what we want to do now is go back and reinvestigate this design and see what we can do to maybe adjust the tolerances, leaving the nominal values to mean values for the parameters the same, adjust the tolerances in order to meet a more favorable probability of non-compliance. So to start this analysis, to do this allocation, all we need to do is, having set up the worksheet in this manner, is go back to the Apogee toolbar. The icon for allocation is to take a response variation and then assign the lower level variation to the individual parameters. So we're assigning or allocating variation to the parameters in this design. So it will ask us which response we want to analyze, and we can do either one of them or both of them at the same time. But since Q was the one we had the most problem with, and for this example and for this tutorial, let's go focus on the Q parameter and see if we could reassign tolerances in order to improve its performance. So we're going to do the allocation for the frequency response Q parameter as a function of the 4 identified parameters. And what's created for us automatically is the statistical allocation worksheet that we can now use to start the allocation task. Okay. So what we see identified for us is the name of the parameter, the cell where this equation calculation resides in our worksheet, the equation result of you plugging the nominal mean values into the equation gives us about 0.76, and we have the previously specified lower spec limit and upper spec limit. Now, to start an allocation, what we're going to be doing the allocation for is in order to predict or in order to achieve a given response uncertainty or a given probability of non-compliance. So I'm not really sure at this time what the standard deviation budget is that I want to achieve, but we can go estimate it. Okay. So let's say that what we would like to achieve is a PNC for this Q response that's equivalent to the PNC that we had for cutoff frequency. And in the prior example, it was 0.003 was that probability of non-compliance. So we can click the estimate button, and we see that a response standard deviation of about 0.006 would give us this result. So let's click OK on this. And now then, using this standard deviation, we'll see if we can achieve then the desired PNC of 0.003. Well, what we see automatically is that we have allocated standard deviations already performed for us. We can see what the respective variance contributions are and mean shift contributions, and we can see that the results of using these allocated standard deviations is a PNC that's very close to 0.003, which is what we desired, which provides the response standard deviation of 0.0066, which is what our budget was. So the allocation has been performed. But let's see if this is really an achievable result or not. Well, one thing we might want to do is let's go convert these standard deviations into tolerances. And for this design, we assumed uniform distributions on our parameters. So we need to put in a tolerance sigma that would be able to allow us to translate standard deviations to tolerances. And for uniform distributions, this would be the square root of 3, or approximately 1.73 would be that amount. So we'll enter this for each one of our parameters. And we can see that the tolerances are being computed for us. But since we really want to view these tolerances in percentages rather than values, the same units as our mean values, we can click this little button up here to convert all of these to percentages. And we see the result is that we wind up with about a 7.3% for the resistor R1, 3.3% for resistor R2, but we need perfect capacitors. No variation is allowed on the capacitors. Well, obviously this isn't a achievable design, so let's see what we can do to go readjust our allocation to get something that would actually be producible using components that we could procure. So in the allocation tool, allocation is accomplished by clicking on this standard deviation contrast. And as we do this, we see that the allocated standard deviations are changing. We're getting slight changes in the tolerance half widths over here also as a part of doing this. And while these are changing, we see that the response PNC is staying very close to 0.003. So basically we're coming up with new allocated standard deviations and the resulting tolerances in order to achieve the result we're looking for. Well, let's go ahead and slide this contrast bar to other values and see if we can come up with designs with non-zero tolerances on the capacitors. And here we see it for this particular selection that we do now have about 1% on the resistors and about 2% on the capacitors, and we've achieved a response PNC of about 0.003. So basically we've achieved the result that we're looking for, and we see that there is a design that will accomplish this with at least components that we could go purchase. Maybe expensive, but we could probably obtain these. Other options we can look at, there's actually an infinite number of selections you can go through. Now at this, as we move the bar down further, we're getting low tolerances on our capacitors but zero tolerances on the resistors. And we can go look at then a range of possible values that would work for this design. So if we decided that there's a particular value of tolerances that we wanted to achieve, and let's let me go find a region here where maybe we can find something we can work with here. Maybe we decide that 2% tolerances is what we want for each of our capacitors. Well, I can go select a cell, let's say on one of the tolerance lines, assign a standard deviation of 2% assuming a uniform distribution, and we've assigned this one. We can do the same thing then for the other parameter and assign a 2% tolerance to it. And we can see then we wind up with about 2% on all of our components using this particular approach. So we see that we do have something that would possibly work and give us a PNC of about 0.003. Now that we've made these changes to the design, one thing I can do is let's move these changes back to our worksheet, and let's go look at all of these as 2% tolerances and then see what the result would be for both Q and PNC. So I'm going to go back to the filter equations worksheet. I'm going to change each of these to 2% tolerances, and since I use cell references in the definition of these parameters and I'm computing these results, here's then the corresponding min and max range for each one and the standard deviations. So now then I can just very simply go re-perform the sensitivity analysis, and we'll do this for both the Q and the cutoff frequency. Get this result, and then the one for the cutoff frequency. So here now we see that by tolerancing with 2% tolerances on each of the components, we have a PNC of about close to 10 times e to the minus 12th on the PNC for the cutoff frequency, and then for the Q we see that we have our 0.003. So this did allow us to, using the same nominal values but now requiring that we have 2% component tolerances, we can actually have something we can go produce and get favorable yields on this individual design. So basically summarizing what we've accomplished at this point is that we have taken a simple Excel spreadsheet. We have defined certain parameters as X's, cells as X's or parameters in our evaluation, certain cells as responses or Y's, and then we were able to go and determine then what the variation would be required on each one of these parameters in order to meet a desired probability of non-compliance for the response for both responses simultaneously. So in summary, we've analyzed the performance, we've performed this allocation as a part of assessing the quality of the design. We did this as part of the initial activity, so it was early in the development process, and now we have a good understanding of what the impact of uncertainty will be on this response and what we can do to do a better job of complying with our specifications. So I hope you see that this activity can be performed as part of your product development, system engineering, design for Six Sigma activities. You can perform this analysis at high-level system parameters or at low-level detail requirements within your design, and determine what the proper tolerancing would be in order to meet the desired objectives. So I'd like to thank you for attending this session. If you have questions or comments, please contact me either by email or by telephone. If you'd like to try this allocation technique on your designs using the SDI tools, you can download the software at stat-design.com. And if you would like information on converting the standard temporary license into a perpetual license, please contact me and we'd be glad to assist you. Thank you very much.